For my final presentation, I will be covering different elements of linear algebra and machine learning. I'm going to start by answering the question, what is machine learning? And then I'm going to jump into basic linear algebra concepts used in machine learning. And then I'm going to talk about one-hot encoding, linear regression, support vector machines, image filtering, matrix factorization, and principal component analysis. So what is machine learning? Teaching computers to analyze large amounts of data on their own by identifying patterns and making inferences based off those findings is machine learning. The reason why we need the computer to identify these patterns is because it is impossible for humans to do it themselves. How do you visualize data that has hundreds of dimensions and then draw conclusions and find patterns from it? You can't, but computers can. And the patterns that the machine discovers have meaning. For example, you can make predictions about the economy based on historical trends, or you can predict when an athlete may regress based on typical patterns found amongst hundreds and thousands of previously collected data points. The system needs a lot of experience and prior knowledge to make accurate inferences. In this way, it's similar to the human brain. For example, humans learn from their mistakes and learn from the past. When shopping, how do you determine what is a good price? Past experience tells you that. So we feed the algorithm an original data set or a training data set, which is a subset of the original data set. So as far as basic linear algebra concepts goes, if you've ever taken a linear algebra course, the data is usually arbitrary or something that the professor made up. In general, matrices are just a way to store data, but specifically in machine learning, each row represents one observation or one row of physical data collected. Or, in the case of image data, each element represents a pixel value. An n by n matrix is an image of size n by n pixels. You will also experience matrix operations, the transpose of a matrix, and eigenvalues and eigenvectors in the world of machine learning. Understanding matrices alone allows you to dive into concepts that are important in the data preprocessing stage of machine learning. One-hot encoding is a method that is applied to all categorical variables in a dataset, because many algorithms and methods struggle to deal with categorical data. There may be bias in models that do not use one-hot encoding techniques. The machine perceives the order of the factors as an ordering relationship between them. So as you can see on the right, apple is assigned to 1, orange is assigned to 2, and peach is assigned to 3. The machine processes them as if the peach is worth more than the apple or the orange, which is simply not the case. There's no value behind those categories. So to combat this, each factor is given its own column in the dataset. 1 is assigned if the column header matches the original value of that observation. Otherwise, 0 is assigned. So as you can see in the bottom right diagram, rows 1 and 3 had apples. So for the first column, under apple, there will be a 1 in columns 1 and 3, and 0s in 2 and 4, and this pattern repeats for orange and peach. So moving on to linear regression. The goal of linear regression is to figure out how much the independent variable x contributes to the variability in the response y. The linear regression equation is as follows. Y equals beta sub 0 plus beta sub 1 times x sub I, for I equals 1, 2 to n. Beta sub 0 is similar to the intercept in the mx plus b equation. So if you look at the equation y equals mx plus b, m you can look at as beta 1. The x vector can be looked at as the x in the mx plus b equation, and beta sub 0 can be looked at as b, which is the intercept. And we're trying to find the most optimal beta sub 0 and beta sub 1 such that for every x, that same beta sub 1 and same beta sub 0 can be subbed into the linear regression equation, and the result will be as close as possible to the corresponding y value in each row. So to do that, we'll consider the equation x times beta equals y. Taking the transpose of x and multiplying it on both sides yields you x transpose x beta equals x transpose y. To solve for the coefficient vector beta, we divide the left side by x transpose x and get beta equals x transpose x inverse times x transpose y, which is equivalent to the beta vector b sub 0, b sub 1, which contains the beta coefficients that we're looking for. And then we can use any value of x that we want and be able to predict the corresponding y value, even if it wasn't in the original data set, with as much precision as possible. Another type of machine learning technique is support vector machines. Although support vector machines can be used to predict in a similar manner to linear regression, it's more commonly used as a binary classification technique, meaning there are only two options for class labels, being positive 1 and negative 1. Our goal is to classify every data point based on its location with respect to the other data points in the xy plane. We can do this by finding an optimal hyperplane that perfectly divides the data by its two classes. It sounds fancy, but in 2D, the hyperplane is simply a line. Properties of the most optimal hyperplane include the transpose of the weight vector times x plus b is greater than or equal to 1 for all points that belong to the positive class yi equals positive 1. Same goes for the negative class. The transpose of the weight vector times x plus b is less than or equal to negative 1 for all points that are a member of the negative class yi equals negative 1. To find the hyperplane boundary that maximizes the margin, we must minimize half times the length of the weight vector squared, subject to the constraints y sub I times the transpose of the weight vector times x plus b greater than or equal to 1. Solving the Lagrange multiplier optimization problem below yields the desired w, b, and alpha sub I values. These values are plugged back into the hyperplane equation, which will give us the equation of the most optimal hyperplane. By substituting coordinate values into x equals x1, x2, which equals xy, and the xy representing coordinate values, into the hyperplane equation, the user can predict which class any given data point belongs to. As you can see in the diagram, PSP represents the positive plane, NSP represents the negative support plane, HP represents the hyperplane, and all the values greater than or equal to 1 are above the positive support plane. So that means all of those values in green are the positive class. And the most extreme values that we mentioned, you can see are right on that positive support plane line. So image filtering isn't exactly a type of machine learning method, but it's still very important to many machine learning techniques. Sizes of digital images can be represented in a matrix P of size m by m. For example, a 100 by 100 image is 100 pixels wide, 100 pixels in height, and has a total of 1000 pixels. Each element of matrix P, P and M, can be represented as a tridimensional vector of the RGB values for that pixel. Using matrix addition to add a vector V to each RGB vector of an image can alter the red, green, or blue channel intensities of that image. The value of F in vector V typically ranges from negative 150 to positive 150 depending on the desired change. Grayscale conversion is a very commonly used technique when dealing with images in machine learning. You can use matrix multiplication from linear algebra to multiply each RGB vector by a linear transformation matrix, T. Each element of T is 1/3 because we are taking the average of the pixel's 3 RGB values, and an example of grayscale conversion could be seen in the before and after image below. One final image filtering example is with edge detection. As we know, taking the derivative is representative of a change in something, and in the case of image processing, it is the change in pixel intensity. Taking the magnitude of the gradient vector results in a single value representing the overall change. Hence, a fast or significant change in pixel intensity results in a high magnitude. At the edges of the image, we would expect to see a high magnitude since the color intensity changes at a rapid rate at those locations. Taking the neighborhood around the center point, f of x comma y, we get the 3 by 3 matrix centered around f of x comma y. There are two approaches to finding the first derivative of f of x comma y, the Prout operator method and the Sobel operator method. Although x detection cannot be solved by linear algebra alone, the Prout and Sobel operator matrices derived above are potential options for kernels in the convolution process for x detection. Pictured below are sample images of X detection on their Prout and Sobel kernels respectively. The next type of machine learning technique that I'll be covering is matrix factorization. And matrix factorization methods are very heavily sought after because they're the driving force behind recommender systems for websites. Recommender systems simply recommend specific products to consumers. I'll be covering two different types of matrix factorization, and the first one being content-based filtering, which takes past actions of the user into account and then makes informed recommendations based on that known data. So looking at the right, we have three tables. A table of people A through D and their preferences regarding car safety and mileage, as well as a table of cars A through D and the safety and mileage ratings for each of them. The first step of content-based filtering is to take the dot product of every row in the person table with each column of the item table, which in this case is the car table. This results in the matrix. So if you look at the person table and the highlights that we have there, person A has a preferred safety rating of 1 and a mileage rating of 0. And if we look at column car B, it has a safety rating of 1 and a mileage rating of 4. So taking the dot product, we have 1 times 1, which is 1, plus 0 times 4 for the mileage, which is 0, and the sum in total equals 1 for the person A and car B combination. And if you notice, the size of this matrix is the number of rows in the person table by the number of columns in the car table. So there are 4 rows in the person table, 4 columns in the car table. We end up with a 4 by 4 dot product matrix. Each dot product element in the matrix will be used to compute the similarity of every combination of user and item using the cosine similarity equation below. As you can see, the dot product that we computed above is used in the numerator, and the magnitude of vector A and vector B are multiplied together on the denominator. Cosine similarity values range from 0 to 1, where 1 implies that the two vectors are identical, and 0 implies that they are orthogonal. A high similarity would indicate that the user may be likely to purchase that specific item based on previous data, so the system recommends it to them. So I mentioned that there are two types of matrix factorization techniques, and the second one is collaborative filtering, which is essentially the inverse of content-based filtering. This process searches for individuals that are maximally similar to one another, and then it uses their preferences as a guideline to predict the preferences of an individual of interest. So as you can see on the right, this time we have the matrix, and we're going to use these preferences to try to predict the individual preferences of a specific person. The steps to collaborative filtering start with normalizing the matrix, then similarity measure is computed for later use, and then the normalized matrix undergoes neighborhood selection, and that's where we identify the maximum similarities between ratings assigned by the users. Lastly, the rating of an item I for a specific target P is predicted based on the known overall rating. So the prediction for any combination of a person and item can be calculated using the prediction formula seen below, where K equals the neighborhood of the most similar items rated by person P, and J is the item being compared to target item I. The final topic to be covered is principal component analysis, and it's really the culmination of all linear algebra concepts wrapped into one. So you'll see eigenvalues, eigenvectors, transposes, covariance, and matrix operations. Principal component analysis is used for the simplification of large data sets. It reduces dimensionality, it allows for more straightforward analysis and visualization of the data, and it saves space and memory. Data needs to first be centered to ensure the data points have a mean of 0. For each sample vector, the population mean, mu, is subtracted and stored in vector B. Then we will find the covariance matrix C, and the covariance matrix will be a symmetric m by m matrix, and since it's symmetric, it can be orthogonally diagonalized. The orthonormal of the eigenvectors are referred to as principal components, and each principal component's direction explains a fraction of the total variance of the data. So you simply find the eigenvalues and eigenvectors like you normally would. And the larger the eigenvalue of an eigenvector mu sub I, the more it contributes to the overall meaning of the data. If a small subset of, say, z eigenvalues are significantly larger than the others, and this typically occurs, those principal directions explain lambda 1 plus lambda 2 all the way up to lambda z divided by the total variance percent of the variation in the data. So what makes principal component analysis so powerful is the ability to reduce data of large dimensions into smaller ones. So as we saw in the last slide, you compute the eigenvalues of the covariance matrix, and then whichever eigenvalues are higher and significantly higher than the other ones, you kind of group together. And suppose for this example, you found that there were two eigenvalues that were significantly higher than the other ones. Then a data set would say 10 variables whose variability can mostly be explained by two eigenvalues, can be reduced from 10 dimensions to 2 dimensions. So it compresses the data to a two-dimensional xy plane spanned by the two orthonormal eigenvectors. And it really enables the use of simple visualization techniques as well as efficient analysis of the data. One application of principal component analysis that I found to be interesting is facial recognition. And a database of banned faces maybe could be collected over time, whether at an airport, a casino, a bar, or any other location where entry may need to be verified. Then you'd convert the images to black and white, and they'd be stored in a vector, where each element represents the brightness of a pixel ranging from 0 being a black pixel to 1, which is white. PCA could be run on the dataset, and the derived principal components could be used to recreate the original image, which is an eigenface, with the highest possible degree of accuracy. So as people walk through the doors for verification, their picture could be taken. Then orthogonal projection could be applied to the image to approximate it as a linear combination of vectors. Each image would be broken down into its eigenface components, and from there, if there's a match with another face in the dataset, perhaps that person would be taken for further questioning or denied entry altogether. And that will conclude my presentation on linear algebra concepts in machine learning.